Okay, welcome everybody. So would you say yes if you can hear me? Maybe not. Okay, so thank you very much. So we're gonna continue our discussions on resolution proof system. So hopefully we can cover the resolution proof system and also talk about the variable elimination, which can be seen as the set solver that you encounter in this course, which is based on resolution. Later, we're going to talk about so-called DPLL solver with closed learning that is, in a sense, a backbone of modern set solver. Okay, so what we covered the last time is that the resolution can be understood as a proof system, but it also is a basis for automated proof system for propositional logic formula. So it's geared, or it's designed to prove unsatisfiability of a formula. But the basis of the resolution proof system is this set representation of CNF formula. So it assumes CNF formulas are given in terms of this set representation. And just to give you a quick reminder, the set representation will represent CNF formula in terms of set of sets, and each clause in the CNF formula will become a set, like a P3 will become a singleton set P3, and then another clause that you see here, P1 or negation of P2, that will be represented as just a set of literals P1 and negation of P2, like the one you see here. And the entire CNF formula will be represented as a collection or a set of these set of literals. Okay. And we said this representation has a nice feature, which is it take care of associativity, commutativity, and idempotence of conjunction and disjunction. So it gives a compact representation of CNF formula. And one important thing that we'll see again and again in the resolution proof system is this notation box that represents the empty set of clauses. So for instance, if my CNF formula will contain box, that means that CNF formula is unsatisfiable because it says that one of the clause in the CNF formula is false. It doesn't contain anything, which means it's equivalent to false. So if we have a false and something, that's gonna become unsatisfiable. So CNF formula contains a box, then it means unsatisfiable. And in some sense, the whole purpose of using a resolution proof system is to derive this box from a given CNF formula. And the key concept or the resolution proof system consists of one proof rule, which is captured by this notion of resolvent. So we said if you're given two clauses C1 and C2, and a new clause R is called a resolvent of C1 and C2. If there exists a literal L in C1 and its complement L bar in C2, such a way that if you get rid of L from C1, L bar from C2, and then take their union, that is the same as R. Okay, so R is obtained from C1 and C2 by just taking a union, but in a sense after doing some cancellation. And this is, this R, given C1 and C2, there may be multiple choices of R, and then just one of the choices called resolvent. And the process of obtaining resolvent from two clauses C1 and C2, that is called by resolution, and it forms the key proof step in the resolution proof system. So so-called a proof in the resolution proof system, or sometimes called derivation, is nothing but a sequence of clauses. So maybe here, showing. Right. So a derivation or proof in the resolution proof system of and then the proof of a clause C from a set of clauses F. So this F is a given CNF formula. And in a sense, we want to derive C. This is, in a sense, our goal in the derivation. And then so it's a bit like we want to conclude C, or derive C from F. And then because it's a formal proof system, we have to specify what constitutes a derivation of proof in this system. A proof or derivation in this system is nothing but a sequence of clauses, so like sequence clauses C1, C2, and so on. And then it has to be a proof of C. So this first condition said what you get at the end should be what we want to prove. So the last guy should be a goal. And then each step of the proof should make sense. That's what the second condition is saying. Each step of the proof, so I is equal to 1 up to m, is either coming from CNF F, the given CNF formula F, which means it can be an assumption in our proof, or this CI should be obtainable from two previous CJ and CK by applying this resolution proof rule. So CI is a reservant of CJ and CK. Okay, so this is the condition that has to satisfy. I mean, using assumption is nothing. It doesn't say anything about the proof system. But this second part is really talking about what kind of rules we can use in this formal proof system. And then in the resolution case, it say that the proof rule we can use is just applying the resolution. It should be the CI should be a reservant of CJ and CK. And particular proof is, well, I mean, we are particularly interested in the specific kind of proof where the conclusion is a box, okay? And that is because this resolution proof system is designed to derive a contradiction, okay? So it's not designed to derive arbitrary clause C. It's specifically designed to derive a contradiction, and it goes very well. Well, in a sense, it captures the idea of proof by contradiction that you are familiar with from, I mean, the high school or in the university. Okay. So the next slide will make these things a little bit more clear. So then the resolution, maybe I emphasize this again. So, and we introduce a specific terminology for the proof of, of this box in the resolution proof system, or derivation of this box in the resolution proof system. That is called refutation. Yeah. I mean, the refutation is a specific kind of derivation, but we have introduced a name. That's because this plays a very important role in the resolution proof system. Okay. And then, as I said, this refutation of a formula F can be seen as the unsatisfiability proof. So it's a proof that the formula F is invalid, is never going to be true, okay? And so this is a specific kind of statement that we can prove about the given CNF formula F, but that is very powerful. That's because of what I said before, which is proof by contradiction. For example, so if you want to prove, this is three conjunction, the conjunction on the left-hand side of this entailment, or this, the semantic implication, left-hand side semantically imply the right-hand side. So what this formula say is, if I give you a reminder, what this says is that for all assignments A, if A satisfies in this part, so then A is also going to satisfy C. So this means semantically, the left-hand side of this, this sign, okay, this sign implies the right-hand side of this sign. Okay, so there is some semantic implication relationship. Now, so this is implication relationship coming from its meaning, and resolution proof system is a specific kind of proof system which can be used to show this type of implication. Okay, so there is a notion of a truth, which is coming from the semantics. There is a notion of a proof, which is a specific methodology to establish the truth. And then we can use resolution to prove this. And the way you can do it is by proof by contradiction, because resolution is specialized for contradiction. To prove this implication indeed holds in using resolution proof system, what you have to do is you take this entire formula in the left-hand side of this sign, this is semantic entailment sign, and then combine it by negation of conclusion. And then if you can derive from there, if you can, from this formula F, if you can derive a box by resolution proof system, or we can, with terminology is we can have a refutation of formula F. So that, we will soon show that if you can prove if you can prove a box using the resolution proof system, that implies the formula is unsatisfiable. So from there, we can conclude this entire formula is unsatisfiable. That implies that, the original semantic implication relationship. This is nothing but proof by contradiction. We take the negation of the conclusions, we conjoin it with our assumption, and then we derive contradiction from which we conclude the Z has to be true. Okay, so just to sum up, the resolution of the proof system is in a sense designed to prove contradiction or to prove unsatisfiability, but because it can be used to show any semantic entailment by using essentially proof by contradiction. So here's just some exercise I want you to think about. So suppose in this specific case, we have a particular, our target formula was just very simple formula, which is just propositional variable Z. But now consider the case where our target formula is Z is not this simple one, but a bit more complicated propositional formula G, okay? So G can be, say, some C1 or negation of maybe P, and maybe negation of X or Y. Okay, so this is a more complicated formula. Now, by still using resolution, which is you can view it as a process that take CNF formula and check whether it can lead to box or not. By using this, we can check this property. Okay, so try to solve this problem. So assume that we have some algorithm that use resolution. So that take formula F, and then it either said, you can't really derive a box in the resolution proof system, or it produces a refutation. In other words, it produces a derivation of box from F. Okay, so suppose we have a procedure like this, and using this procedure, try to implement the procedure that check this entailment relation, semantic entailment relationship. So I will give you 2 minutes to think about this. Okay, so let me show you how to do this. It's not very difficult. Erasure. So maybe erase this part. Okay, so suppose G have this form. Let's just think about something. I think this just knowing one case, it should be good enough. If we have a, maybe it's better. Suppose we have liters L1, liter L2, and L3, and liters L1 prime and L2 prime, maybe L3 prime. Okay, so it can be, there are maybe more liters in each clause, or we may have more clauses, but it doesn't really matter. This will shows how you can translate this semantic entailment into the type of questions that the resolution proof system can take care of. So one thing you can do is F semantically implies G that is identical to F semantically implies L1 or L2 or L3, and F semantically implies L1 prime, L2 prime, and L3 prime. Because G is a conjunction of these two guys, this semantic entailment about F that semantically implies G precisely when F semantically implies the first conjunct of G, also F semantically implies the second conjunct of G. So this can be proved using semantics that we learned before. Now, if for this case, we can prove this semantic entailment by proof by contradiction. Okay, so this one can be checked. So to check this, we can invoke the resolution prover. So let's say res proof with F extended with negation of this entire thing, but negation by De Morgan's law is, is a conjunction of literals. Okay, literal itself can be seen as a clause, so just clause with only single literal. So we can just put them by taking their negation. So we can take the L1 bar, which is a negation of L1, and then to L2 bar and L3 bar, and then we can check whether that leads to contradiction or not. Okay, so that's one thing that we can invoke. And then the final outcome shouldn't be only rely on this guy, should also check the second case. So we said, I will use the notation from Java. So we just say double ends and call resolution prover. The second case, which is F, to essentially the same thing, L1 prime bar and L2 prime bar and L3 prime bar. So if by calling this, we can check, is this a second property? Is checked by this. The first is checked by this. So what I wrote there is a way to check this semantic entailment between two any CNF formulas by using resolutions or reformulating this semantic entailment between two any CNF formulas in terms of unsatisfiability questions of CNF formulas. Okay. So now let's analyze the properties of the resolution. So one way the starting point of the analysis is to think about the res operator. So this is not an algorithm. You can implement it as an algorithm, but it's more like a mathematical operator. Okay. So this mathematical operator res, and then we're gonna define two things. One is called res. The other is called res star. So what res does is that it take a set of clauses, or it take a CNF formula expressed in terms of set representation. So you take f, and then it increases f by considering all the resolvents that can come from f. So you take the rest of f is same as f together with all the r, that r is just resolvent of two clauses in f. In other words, what this means is that from f, we apply the proof rule of resolution either 0 times or once, and then we collect all the possible consequences that we can obtain there. So it's something that we can obtain by applying resolutions proofs by 0 times and 1 times on f. Okay, so that's what the rest represents. And then now this rest superscript 0 or superscript n plus 1 attempt to capture this notion of what we can get if we apply the resolution proof system or resolution proof rules 0 times or that means just once or twice or 3 times up to n plus 1 times. So that's what this res superscript n plus 1 try to capture. So res superscript 0 try to capture that what we can obtain by applying resolution like nothing, no times at all. So then that has to be same as the given formula, the CNF formula F. Otherwise, so if res n plus 1, it is something that we can obtain by first applying res n, so that this will give us all the consequences of from F, which can be obtained by applying resolution 0 times, once, twice, up to n times. Okay. And then if we apply res one more time to the entire outcome there, then they will increase, they will consider one more possibility. So it will give us all the consequences that can be obtained by applying resolution up to n plus 1 times. So that's what's written here. And then res star is obtained by taking the union of all of those. So which means it's collecting all the consequences of the resolutions on the formula F, where we apply the resolution proof system infinitely many times. It can be 0 or once, twice, and so on. Okay, so that's what res star say. And then so this res star, in a sense, captures what we can actually derive by applying the resolution on the formula F. Okay? So then there are just some very easy consequence that we can show. But I want you to prove this statement. It say that if a clause, it belongs to this res star of f. So res star is like a, operator that you can actually implement in a, say in Java or Python. Okay, this is a operator. It may go on forever, so it may not terminate, but it's an operator that you can define. So we said if C belongs to this, this is operator, precisely when there is a derivation of C from F in the resolution proof system. Okay, so try to prove this theorem. So I will give you maybe 3 minutes to think about this. It's in a sense obvious statement if you are familiar with doing, dealing with this type of system, but doing a proof of this kind, it can give you a good practice. Okay, so let me show you how to do this. Okay, the proof is by induction. So let me move this a little bit and maybe clear. So the proof is by induction. And then, so we prove that this side of the implication is true first. So that we say just pick C, which is in res star of F. Then because res star of F is a union of n greater than 0, res n of F, by the definition of union, there should exist n such that C is in res n of F. So this is always the case. I mean, it's a union, then it has to belong to one of them. So what we're gonna do is we will do induction on n. So the base case, if n is equal to 0, n is equal to 0, in that case, the res 0 of f, same as f. So what that means is that C should belong to F. So then there is a resolution there, I mean the resolution proof or derivation of C in the system, which is just, so in this case, so we can use just a singleton sequence of C as a derivation of C from F. Because the only condition about derivation is the last guy should be equal to our conclusion, which is the case here. And every step should be either assumption or should be obtainable from the resolution proof rule. And here C is an assumption, so that's no problem at all. So that's our base case. Now for the inductive case, so we said n is greater than 0. So then we know that C should belong to res applied to res n minus 1 and F. Okay, and if I unpack the definition of this guy, so okay, so the definition said that's same as res n minus 1 or F, or some older reservants. So R is a reservant of two clauses obtained from res of F at res n minus 1 of F. So we do, I mean, I'm gonna go very details just to make sure although it's really simple. So then there are two cases. One is C belong to res n minus 1 of F, or C is a reservant of, so do you see any problem here? Okay, so I think, so somehow something happens. It's somehow all the students became unmuted. So is everything okay? Would you say yes? Okay, so yeah, I mean, I heard that sometimes some hackers interferes with online lectures and do something funny. I hope this is not the case. Okay, so I'll just continue. If you experience any problem, please shout. Okay. So if there are two cases, either C is a resolution from the n-1 step, or C is a resolution, is a reservant of, so it's a reservant of some C1 and C2, that they are coming from res n-1 over F. Okay, so this case, we can use induction hypothesis and then say there is a derivation in the resolution proof system from F to the conclusion C, because we have n-1, and so we can use induction hypothesis. In this case, we again use the induction hypothesis, but induction hypothesis tells us, so for this case, we can use induction hypothesis, but induction hypothesis say there is a resolution proof of C1, which is a sequence of clauses, and the last guy is equal to C1, and then each step is either assumption or derived by resolution proof rule. And also there is a proof derivation C2 by the induction hypothesis, because both of them belong to res n-1. And then the way to construct C is just put these two things together. So we just put, to construct the derivation, we put these guys for C1 and then put these guys for C2. And then last, we just put C at the end. And that is okay because the conclusion is C. And every step that goes from here and every step that goes here are justified. They are either assumptions or obtained from resolution proof rule. The only missing justification is for C, but C can be justified by the resolution from the C1 and C2, okay? Because that's our assumption that's here. So C is a reservant of C1 and C2. So that's how you can prove this one side of the implication. And for the other side, yeah, so actually the other side is, okay, so for the other side, we now, so suppose we have a derivation of C in F. So we have a derivation of C from F in the resolution proof system. So what we're gonna do is that we will look at the length of this derivation and set it to n, and we're gonna do induction on it. Okay, so if n is equal to 0, so then if n is equal to 0, right? So then the C must be an assumption. So that implies that C is in res 0 of F. That is a subset of res star of F. There's no problem at all. So that's the base case. The inductive case is, now consider the case that so this n is greater than 0. So in that case, what we do is that we look at possibility. We also do case split if C is an assumption. Maybe a better way to say this is, because C should be one of the steps in the derivation, it should be either assumption or obtained by applying the resolution proof rule. So the first case is if C is in F, then we are done, the same as before. So we can use essentially the same reasoning that's going on here, or there's another case which is, C is obtained from two resolvents, which means that in the derivation of this guy, somewhere there is a Ci, somewhere there is a Cj, such that C is obtained from applying the resolution proof from on Ci and Cj. So in the more tree-like notation, there is this Ci and Cj and C. Okay, but now because the Ci and Cj appears before, and then also, this step can be understood as a derivation of Ci, and this step can be also understood as a Cj, and they are shorter than n. By induction hypothesis, Ci and Cj both belong to res star of F. Okay. And because res star of F is a union, so there is Ci, and then the Ci belong to some res M1 of F, Cj to res M2 of F. Now, although I didn't really show this, and something very easy to check is if you take a maximum of these two, so these two sets, and both of them will be a subset of max of M1, M2 of F. Because if we increase the superscript, it will always make sets larger. Okay, so this is the case. Now, what we know is if now apply res on res max of M1, M2 on F, that we should contain all the resolvents of two clauses that belong to this set. So in particular, that should contain C as well. Okay, so that's how you can prove this. So we are doing induction on the length of the derivation. So this is the length of the derivations. So the length for Ci, because it's a sub-derivation of C, it should be shorter than n. The length of the derivation for Cj, which is also just kind of subsequence of the entire derivation, it should be shorter than n. So that's why we can apply induction. Okay, is it okay? If something is not still clear, just ask questions. Okay. So I'm saying to somebody who is not familiar with doing kind of formal reasoning with this type of proof system, it may be confusing, but the proof itself is not very hard proof. Okay, let's move on. So now this resolution proof system now we analyze the power and correctness of resolution proof system. So it satisfies so-called soundness and completeness. Okay, intuitively, soundness means anything proved in a proof system are correct. I use the word valid here, but really it means anything proved is correct. The proof system never lies. So that's what soundness say. Completeness means that anything true can be proved. So proof system is like a mechanical system that, it's a very systematic strategy of constructing a proof. So soundness say that systematic strategy is correct because it will never let you prove something wrong. Completeness say it's very powerful. By using it, you can prove essentially all the true things. Okay. In the case of resolution, although I wrote it in this validative form, I think the easier way to understand what really happened is that if there is a resolution refutation of F, if and only if F is unsatisfiable. So this is equivalent to saying F is unset. So this equivalence tells us is that as far as showing unsatisfiability is concerned, resolution proof system is never lies, and also it's very powerful. It can let you prove everything. Okay, that's what this statement is telling us. Okay, so we're gonna prove this soundness and completeness, and the key. So we'll first look at soundness. The key step of the soundness is this lemma, sometimes called resolution lemma. Okay, the resolution lemma say that if F is a CNF formula represented as a set of clauses, and R is a resolvent of two clauses, C1 and C2 in, two clauses of F, then F and F together with R, so F conjoined with R, so because it's a set representation, this is just represent conjunction, they are semantically equivalent. So F semantically implies the right-hand side semantically implies on the left-hand side. So the one side of this implication is actually quite easy. So this F union R, as I said, this is this F union R. This is same as for more logic notation, taking F conjoined R. Intuitively we strengthened the F with R, so that should imply F. More formally, you can show that for any assignment satisfying F conjunction of R, then that's because it satisfies conjunction, it should satisfy each conjunct, so it should satisfy F as well, by the semantics, by the meaning of this conjunction. So showing this is obvious, but showing the other direction is actually requires some more thinking. So here I want you to do this. So I will give you maybe 2 minutes to try to prove this other direction. Okay, so let's look at the proof. Okay, the next slide actually explains this, but I think maybe handwriting is a bit better for the proof here. So we want to show that this F semantically implies F conjunction with R. But this means what we have to show. So we have to prove So F implies R. Okay, so but to show this, we use the assumption that R is a reservant of two clauses from F. So we have so R is a reservant of C1 and C2. They are in F. Now we consider the assignment of variables, so which maps all the variables, propositional variable to 0 and 1, such that, I mean, maybe writing one better. So we consider assignment A such that A satisfies F. Okay. By the way, because R is a reservant of C1 and C2, there should be a literals which are canceled when we obtain R from C1 and C2. Let's call that literal as a L1, the literal in C1, let's call it L1. And then that means there should be its complements should be in L2. L1 may be a negation of propositional variable. That's completely okay because this complement is just removing this negation sign. Okay, so it's just they are in a complementary relationship. Okay, so if that is the case, so then we have to prove that A also satisfies R. But to show this, we do case analysis. If then A should be in satisfy L1 or A should satisfy L1 bar. And that's because, I mean, they are complementary relationship. One of them must be true. Now, if the first case is true, if A satisfies L1, so that means, A should satisfy C2 minus L1 bar. Why is that? Because C2 is a clause in F, and all the clauses in F should be true under A. That's because of this assumption. Like A satisfies everything in F. In particular, A satisfies C1. Also, A satisfies C2. But we know that A doesn't. So this is C2. If I expand the C2, it's gonna look like it has a bunch of disjunction, and one of them will be L1 bar. But we know A satisfies L1, so A will never satisfy this guy. Okay, so then that means A will satisfy one of the remaining ones. So that's what this condition is saying. By the same reasoning, if this happens, A satisfies negation of L1, well, complement of L1, then A will satisfy C1 minus L1. Exactly the same reasoning. A should satisfy C1, but it can't satisfy L1, the one of the literal there, so that it has to satisfy one of the other remaining literals. Okay, so that is what we obtain. So in this case, because A satisfies C2 minus L1 bar, but what we know is that this guy is a subset of reservant R, because R is obtained by C1 and C2 after cancellation. So this one describes the cancellation. The same way, the second case, this one is belonging to R. So because this means this subset relationship means that R has more disjunct. So A will satisfy R in this case. Also, A will satisfy R in the other case. Okay. So really the key step is that we do case analysis on the canceled L, and that case analysis guides us whether R is gonna satisfy something from C2 or something from C1. Okay, and that one of them is always true, so that's why the A will always satisfy R. So that shows so we pick any A that satisfies F, that any A in either of these cases satisfies is also going to satisfy R. So therefore we can conclude that F entails R, and that's going to be the proof of the other implication. Now, again, nothing hard, but it involves some case analysis, And that case analysis corresponds to applying the resolution. Okay. So that here's a proof about this, but that's exactly what I told you. Now, by using this resolution lemma, which is whenever we apply the resolution proof rule and construct reservant from existing clauses, we are not changing anything. So you're just adding this reservant to the existing formula, given equivalent formula. So that's what we proved. And then the soundness follows from this resolution, this resolution lemma. Okay. So soundness to say that if we can derive a box from F using resolution proof system, in other words, if there's a refutation of F in the resolution proof system, then this F has to be unsatisfiable. And that can be proved by resolution lemma. Yeah, I can show you this. Yeah, maybe again, just say what it said. The proof is quite simple. So if we suppose we have this derivation of a box, so that means, so suppose there is a derivation, which is C1, C2, and so on, and we end up with a box from F. So then, yeah, maybe this say Cn-1 and box. But that means the each of Ci's, they are already in F, or they are obtained from by applying the resolution proof rule for the clauses appearing before. Okay, so it's either from F or some obtained from some clauses from before. So that means that and the resolution lemma, what this entails is that F should be logically equivalent to F together with all the clauses in this derivation, C1, C2, and so on, and the box. And that's because if Ci is already in F, this doesn't mean anything. If Ci is obtained from the resolution by the resolution lemma, this semantic equivalence is going to be maintained. So we can show this equivalence is true. Okay. Any proof step preserve the semantic equivalence. So that's why we have this semantic equivalence. But now once you have this semantic equivalence, what this means is but now if there is some A, okay, this is semantic equivalence. What this say is that for any A, if some assignment, A satisfies F precisely when A satisfies F conjunction C1, conjunction C2, conjunction Cn-1, and box, which is false. Okay. But then you can see, the box, which is false, will never, will be satisfied. False is always false, so it will never be true. So then this part will never be true. So that implies this part will also never true. What this means is this F is unsatisfiable. So that's how you can prove this resolution, this soundness statement. Okay. So just to sum up, soundness is say if our proof system never lies, so whatever you do, proof system, you will always obtain correct outcome. In our context, if we prove contradiction, in other words, if we have a refutation from some formula in the resolution proof system, that formula should be unsatisfiable. And then that statement follows from our resolution lemma, which say that essentially the resolution proof step never changes anything. It just transforms logical formula into something which is equivalent. Okay. So now So then the more interesting part is completeness. Completeness is the opposite of the soundness. Okay, so you say if a given CNF formula is unsatisfiable, then we can derive the empty clause, but we can construct refutation from the formula by resolution. Okay, so this say that our resolution proof system is extremely powerful. Whatever unsatisfiable, we can always prove it its unsatisfiability using resolution proof system. So, and then my friend said the soundness and completeness are really talking about syntactic proof correspondence between syntactic proof system, which is like a resolution, and semantic truth. So completeness says semantic truth implies, in this case, unsatisfiability. Semantic truth implies the syntactic truth, which is a derivation of a box in the resolution system. Soundness talk about the other direction. Okay. So actually, our resolution proof system is complete. And then the proof of the completeness is a bit more involved. Okay, so our is a completeness say formula is unsatisfiable, then we can derive a box from F. And it's a bit involved. So what I will do is that I will show you a little bit of it and give you some time to think about the more challenging step. I mean, I know it's challenging, so it's maybe not entirely obvious, but if you take some break and think about it a little bit, that may help you to understand what I'm going to explain. So then the proof is doing by induction on the number of variables in the formula F. Okay, so if I given a formula F, there will be a fixed finite number of propositional variables. So we're going to do induction on the number of variables. And our assumption is that this F is unset. I mean, we are starting from unsatisfiable F. And then our goal is to show by doing inductions, the refutations. So this is a given. Our goal is to construct refutation. In other words, our goal is to derive a box. Okay, so how to do this? The base case is relatively okay. So if n is equal to 0, which means my propositional this formula doesn't really contain any variable at all. And there are actually only two possibilities. Either F itself is an empty set, okay, or it contains only one empty set. So F is either one of two cases. One case is F itself is just like this, or F is equal to box. Because it can't really use any propositional variable, these are the two only possibilities. But because F is unsatisfiable, this case cannot happen because this one is always a satisfiable case. Only this case can happen. And in this case, because the box is already one of the assumptions of F, I mean, remember the box represents false, which is the same as it's another empty set. So in this case, this is the only possibility. And in this case, we can construct the refutation by just writing a single sequence, which is a box. Okay, so constructing single sequence in this case is quite easy because I mean this is the only possibility. Now for the inductive case, it's a bit more involved. So think about how to do the inductive case. Okay, so let me give you some hint about how to. So to do the inductive case, now the induction is over the number of variables. So given a formula F, you should be able to construct something which, in a sense, decreases with respect to this measure of the induction. So we are given F. So we have to construct something that over which we can apply the induction. Now consider the two something that you can do. One is for F, you replace propositional variable like nth propositional variable by false, and then do some simplification. Okay, so that's gonna be, I mean, yeah, so if you do the simplification like hit this, so this will be a formula where the measure of induction will be decreased by 1 at least. And then the another things that you can do is you replace it by true, Pn by true, and then this, again, the measure of the induction is decreased by 1. Now, if F is unsatisfiable, so then these two guys should be also unsatisfiable. I mean, if one of them is satisfiable, that means by plugging in false, mapping Pn to false will give a satisfying assignment of F. So that's not possible. Unsatisfiability of F implies this guy is unsatisfiable. This guy is also unsatisfiable. So this one uses at most n-1 propositional variable. This one also uses at most n-1 propositional variable. Both of them are unsatisfiable. So we can apply induction hypothesis to construct the refutations in this case, another refutation in this case. Now, somehow find some way to, from these refutations, find some way to construct refutation of F. That's the key step of this proof. And so try to finish the proof of here, of this. So what I will give you maybe 2 minutes to think about this. Okay, so let me give you the proof. So now what we, I mean, if you just click buttons, then you can see the proof there, but let me also explain this by handwriting. So as I said, I mean, these two cases, we can apply the induction number of variable is decreased by at least 1. In this case, also decreased by at least 1. So we can apply and then both of them are unsatisfiable, so we can apply the induction hypothesis. Now, if you apply the induction hypothesis, that will give us a derivation of a box. So derivation of contradiction in this case. So if you apply the induction hypothesis will give a derivation of a box here. And let's just make it more explicit. So we have C1, C2, Cn, and then box. Also, if we apply the induction hypothesis, we get maybe C prime 1, maybe let's call it D. D1, D2, DM, and box here. Here we apply the induction hypothesis. So our general proof scheme is to construct the refutation of F from these two guys. Okay, so now if you look at C1, C2, Cm, and let's just say we want to claim this is a refutation of F. What we think about what could be a problem. Conclusion part is okay. The conclusion is a box. That's what we want. But maybe some of the steps, and also if the sum of the step uses resolution, that's also okay. But the problem is if the sum of the step uses assumption, okay? So if, say, C2 is using assumptions from F where Pn is replaced by false. So that assumption may also, so that's a clause in this F with this change. That clause may appear in F or maybe appear in F with some extra things, which is a negation of Pn. Okay? I think the better figure is just maybe showing some examples of F. So if you have F, say Q or negation of Pn and negation of Q, okay, that's N or Pn. So suppose we have a formula of this kind. I raise here. And so then after this is F, then after this replacements, I mean, this becomes false, this becomes false, and having false as an additional disjunct doesn't affect anything. So that becomes the same as Q and negation of Q. Okay, so in this case, if you apply, maybe apply the induction hypothesis, the induction hypothesis might give us derivation, which looks like a Q, negation of Q. So this is one clause, this is another clause, and then box, because this box is obtained by the resolutions. I mean, it's a reservant of clause P and the clause Q and clause negation of Q. So that's the kind of situation that's appearing here. Okay, so maybe the one possible problem is some of the clause in this derivation, some of the clauses that we use is actually maybe that same clause appears in F, then there are no problem of converting this guy to a derivation in F. But some of the clause like Q is not really appearing in F. Instead, what appears is a Q together with this disjunction of a Pn. Okay, so what we do is that we translate. Okay, so this is the part of some observation. So what we would gonna do is that we're gonna translate this guy to some we translate it by adding the or Pn whenever it's necessary. So for instance, we're gonna add C1 and C2 union Pn. So C1 is in original F, so then we just keep it as it is. And then this one is not in original F, but if we add the Pn is original F, then we just add it like this. And also in the step maybe Ci, that is obtained by, I mean, two of the clauses before, but these two clauses, one of them, in this translation or conversion phase, one of them ended up with having Pn. So then we add Pn there. Otherwise, I mean, if it's again the reservant of two steps before, but none of them during this translations requires adding Pn, then we just leave it as this Cj. Now that process continue until the last step, which is a box here. Okay, this guy. But we have a two possibility that box may be changed into Pn. So that's a one possibility, or the box may remain to box. So these are the two possible ways of ending this. So in other words, taking this refutation proof or derivation, and then we add Pn whenever it's necessary to convert this derivation from this guy to the derivation from original f. Okay. Now, if we end up with this top case, then we are done. I mean, this is the derivations from f that leads to box contradiction. So we have a refutation, so we are done. Otherwise, we go get this bottom. So then we just leave it as it is. And we apply the same thing for this second part of the derivation. Now, this time, because we replace Pn by true, we're going to add negation of Pn. I mean, we're going to think about for each di is an assumption in f. We just leave it as it is. Di is an assumption, not an assumption in f, but it is an assumption when we add this negation of Pn. Then we add this negation of Pn there. So that change, that's gonna lead to another change, which is gonna be d1 prime, d2 prime, and so on, dn prime. And just like before, we have a two possible way of ending this. One is either we end up with negation of Pn or box. So just like before, if we end up with box, then we are done. Now, otherwise, we are living in this case. Okay, we are left with this case. So what we do is, if we are left with the other two cases, which is we have this derivation from f. Also, we have this derivation from f. So now if we put these two derivations together, then we end up having a derivation of some Pn. So that's coming from here. Also, we have a derivation of negation of Pn. That's coming from this side. So then if we have, I mean, this is the derivations from f. Now what we can add box in this step, that's because we can apply the resolution proof rule to this Pn and negation of Pn. Okay. So that's how you can conclude the proof for this guy. It's a bit involved, but the idea is you can construct a two inductive case. Each case, we have a derivation of a box. So we have one derivation that's coming from one induction hypothesis, another derivation coming from another induction hypothesis. And then our proof strategy is convert this derivation from these clauses to the original clause f original formula f that we started with. Okay, so that's the translation. If the translation gives a refutation of f, then we are done. Otherwise, we can combine the translated derivation to construct refutation of f. That's how we do the proof. Okay, just give me 1 more minute, then I will finish it soon. So here's a proof about this that explains what really happens there, but that's correspond to what I said. And here's a more kind of things that's really going on. So this is the case for false. So if we start with the formula f, so this is a formula, it's a conjunction of these guys. Then if we plug in false, so if you plug in, so suppose R is what I call Pn in the previous slides. If we plug in false, so then some of the cases just disappears. This one is true automatically. This one means this clause also disappears. Now, in this case, because fr is a false, this disappears from the clause. This also disappears from the clause. So the remaining part is the one that I wrote as f false. Where R is replaced by false. So then we can derive construct refutation from here. This is a refutation proof. that can also be represented as a sequence. Okay, so then the key step of the proof was to convert this refutation to some derivation, which is a refutation of f false given r. The key step is converted to a derivation of something, some clause C from f. And the key step of the way we do it is we insert R in appropriate places. Okay. So because this guy is an assumption originally from F, we don't do anything here. But for this guy, it's actually coming from P together with R. So we restore R by plugging there. And because R is added, all the consequences will also contain R here. For negation of Q, we will have the same situation. Originally, it contained R. So what we're gonna do is we add R there, and then the final step of the entire rules will give a clause which contains R. And we do the same thing for the other case where R is replaced by true. Then by combining these two, I mean, either we end up with a proof of refutation proof of original F, or we can combine two converted translation, the derivations to construct refutation of original F. Okay, so that's, sorry for overtime. So that's it for today. I'm gonna stay here for 5 minutes. And then next week, we're gonna talk about how to create an algorithm from this refutation proof system. Okay, thank you very much. Also on Wednesday, we are not going to have any lectures at all, any lecture at all. I mean, it's an election day. I think I encourage you to go and vote. Okay.